Well, welcome everyone to the Western Hemisphere Virtual Symplectic Seminar. We're happy to have Marco Castronovo from Rutgers, and he'll tell us about the Fukaya category of Grassmannians, bootstrap, and mutation.
Okay, so thank you very much for the invitation, and thank you for organizing this virtual seminar that has kept the community alive throughout the pandemic. Yeah, I'll be talking about work that I've done in my thesis at Rutgers. So it's part of a program that might succeed, might fail, who knows, but whose final goal will be to prove that the Fukaya category of complex Grassmanians is split generated by Lagrangian tori. So somehow it's an attempt not to establish some general result about structural invariants in symplectic topology, but to figure out how to compute them in a hopefully interesting class of examples, and how to understand mirror symmetry in these examples. Okay, so yeah, we'll start indeed with some context of this kind of math. So the context is Fano-Landau-Ginzburg homological mirror symmetry along the lines of Koncevich's proposal, and also work by Horik Balfa on D-branes, and Kapustin. These are physicists, and many other people, of course, have been part of this circle of ideas. Let me open the chat so that I'm sure I catch all the questions, but feel free to unmute yourself. Okay, so we have two sides. On one side, it's X, which is a Fano manifold, so complex projective variety, smooth with ample anti-canonical bundle, and we have a given choice of anti-canonical divisor D. And I'm going to think of this projective variety as a symplectic manifold with the symplectic structure induced by this choice of divisor. And a classical, well, a quantum, but already a classical invariant attached to this manifold is its quantum cohomology ring, let's say over C. And on this ring acts an operator, the multiplication by the first Chern class of the tangent bundle. And this operator has some eigenvalues that I'm denoting lambda here, with lambda here. And on this side, we have a categorification of quantum cohomology given by the derived Fukaya category of branes with charge lambda. And so very roughly, what this is a category whose objects the construction starts by considering objects that are Lagrangians, endowed here with rank 1 local systems that I'm denoting by Xi. And these local systems allow us to define a twisted version of Lagrangian fluid cohomology, where counts of pseudomorphic disks are weighted by the holonomial of this local system. So charge lambda means that we only consider those local systems that satisfy this equation. So when we take the count of Maslov 2 disks in a given class beta, and we sum over all beta weighting by the holonomial of this local system, we require this to be lambda. And the reason why we do this is that because these are Lagrangians in some compact symplectic manifold, in general, there will be the Flory differential will not square to 0, and so we need some condition. We need this local system to kill somehow the curvature of the Fukaya algebra. Okay, so and so I'm not going to describe hump spaces, but let me go straight to the mirror. So the mirror is supposed to be an algebraic variety over C. So this is a peculiar expectation of the Fanos case. In general, one would be expecting some rigid analytic space over the Novikov field, but here it's expected that the mirror is convergent. And this mirror should carry some global function, W, called Landau-Ginzburg potential. And essentially, the philosophy is that the critical values of this function should match the eigenvalues of this operator on the other side. And the critical locus of this function instead should have a triangulated category associated to it that matches the derived Fukaya category. And this category has been studied by Orlov and others. It's the derived category of singularities. Yeah, and so mirror to a Lagrangian should be some subscheme of the mirror. Let me denote it by U. And the mirror to a local system on the Lagrangian, a rank 1 local system, should be a point of this subscheme. And the condition that for cohomology of this Lagrangian is non-zero should be mirrored to the fact that this local system thought as point of U is a critical point of W. And the curvature condition on my object of the Fukaya category should be mirrored to the fact that under the function W, Xi maps to lambda. So this is the basic philosophy. I'm not really talking about math here. I'm just outlining a philosophy. Okay, so in the toric case, this has been studied and understood, starting with the work of, I would say, I would mention just a few people, and then of course many others worked on the topic. So Cho and Ho, and Fukaya Ota Ono. And of course, many people worked on the other direction of mirror symmetry, but I'm not looking to that today. So in this case, the dictionary I depicted about specializes in this way. So X is the toric variety associated to some polyhedral fan lambda, and to each ray rho in this fan is associated a prime torus invariant divisor D of rho. And the sum of all these divisors is what's called the toric antagonal divisor. And to this divisor is associated a polytope, which is the set of points in Rn where when we pair, when we take the dot product of those with vectors that are primitive generators of my rays in the fan, and that's at least -1 for rho, then this defines a convex polytope. So here in this picture, you have the polyhedral fan of CP2. These are the primitive generators of the rays, and this is the polytope you get if you write down this polytope. Yeah, and so in this case, there are some natural Lagrangian tori, which are the fibers of the moment map. So here I depicted the fiber over, let's say, the origin in this polytope. So a basis of Z to the N in the target of the moment map lifts to a basis of cycles in here in red and blue for any moment fiber. And we can count holomorphic disk or J holomorphic disks if you perturb J with boundary on this Lagrangian torus, and given and there for given boundary homology classes there are disks that hit the toric divisor depicted in orange here. Yeah. So on the other side, a proposal that I think was first given by Hori and Bafa is that the mirror of this should be a complex torus of the same dimension as the target variety, so C star to the n. The Landau-Ginzburg potential should be a Laurent polynomial with one monomial for each ray of the fan, so x to the u rho in this case. And somehow mirror to this polytope here, this moment polytope should be a polar dual polytope, which is the Newton polytope of this Laurent polynomial. In other words, the convex hull of these primitive generators here. And here's a picture for CP2. And so, and this Laurent polynomial has essentially one monomial for each Maslov two-disk, rigid Maslov two-disk in the picture. And here's an example of how you would think of CP2 in terms of the mirror. It's a function on C star squared with 3 critical points and 3 critical values. And these critical points, they match 3 local systems on the fiber of the the moment map that make flirt homology non-zero. Okay, so today I'm going to talk about another case, which is the case where X is a complex Grassmannian of K-planes in Cn. And so other Fano examples have been investigated. So I'll mention the work of Sheridan for the case of Fano hypersurfaces in CPN. From the work of Sheridan, one could naturally explore the case of Fano complete intersections, but somehow what I'm doing today goes in an orthogonal direction because Grassmannians are, again, an infinite class, but typically they're not complete intersections. So if you take a large enough Grassmannian, at least in the Plucker embedding, it's not a complete intersection in a CPN. So somehow, if you want to explore mirror symmetry in the Fano case, you're looking for infinite classes of examples where you might have a strategy to figure out what's going on, and somehow this is a natural class of examples to look at. There's also a feature of this class, which is that it's a subclass of a larger class of the so-called homogeneous varieties G mod P. So the feature of this class of examples is that we do have a candidate Landau-Ginzburg model, which is essentially really the first step to have a guess for the model if you want to typically study convergent mirrors. So this model now doesn't really come from physics. It has been proposed by Peterson and Rich, and the ideas involved in the construction of this mirror come essentially from representation theory. So G is some complex algebraic group, and it has some Langlands dual group G dual, and the parabolic P has also such a dual, and there is an affine open affine variety in here called the open projected Richardson variety, and that somehow people in representation theory have been interested in before mirror symmetry. What Peterson and Rich proved at different levels of generality, but essentially now in full generality, is that the quantum cohomology of G mod P matches the ring of regular functions on the critical locus of a certain function on this affine variety. And so there is a strong mathematical instead of physical evidence that this is a correct mirror, at least from the point of view of closed string mirror symmetry. Other features that might make this class of examples interesting are the fact as are the following. So the ring of regular functions on this affine variety is known in many cases and perhaps expected to, in all cases, to admit a so-called cluster structure in the sense of Fomin-Zelevinsky, and this existence has been investigated by Leclerc and others. So what this means essentially is that this variety is endowed with a almost atlas up to dimension 2. It's endowed with an atlas of complex torus charts, just like in the tori case, but now many charts related by birational transition maps of a very special kind. And this somehow seems to suggest that there should be plenty of Lagrangian tori in G mod P that could potentially be interesting to study. Yeah, and there is also, in this case, a direct connection with the Gross-Zieber program. I will not say much about this, but there were some conjectures about the structure constants of these algebras, these cluster algebras, about especially positivity of certain structure constants. And I think my screen froze. Let me try to update. Yeah, now it works. Yeah. So what Gross, Haken, Keeley, and Kontsevich did was to, starting from the notion of scattering diagram that was previously introduced, they essentially redefine cluster algebras in a way where this positivity could be a consequence of geometric interpretation of the structure constants as tropical curves. And so there is some indication that there is a connection with scattering diagrams. There is a connection with the Gross-Zieber program, and these tropical curves seem to be related to J-holomorphic disks in a way that is maybe more precise than other classes of examples. Okay, so let me give you a panoramic view of the state of the art until at least, I guess, a couple of years ago on the understanding of mirror symmetry for Grassmanians. So I'll mention three trends, what I call cross-stream trend. So people who studied, as I said, the quantum cohomology of G mod P and in particular Grassmanians. As I mentioned, it was checked that it matches the Jacobian of a certain function on the open projected Richardson variety. Then Marsh and Rich so essentially took the Lie theoretic definition of this W that I haven't given to you yet, and they turned that into something very concrete in terms of Fluker coordinates in the case of Grassmannian. And this will be the start of my work that I'm describing today, the starting point. And then Rich Williams, they started to study the restriction of this W to several of the cluster charts of the mirror, and in particular their Newton polytopes and their polar duals. So if you remember, I think my screen froze again. Yeah, so if you remember what I said before, there was a polar duality relating moment polytopes and Newton polytopes in the toric case. So from a combinatorial perspective, Rich and Williams investigated the Newton polytopes of Laurent polynomials that one gets by restricting W to different cluster charts. And they discovered that they're polar dual to polytopes on the other side that are known as Auchencode bodies. and somehow generalized moment polytopes. So then there's a so-called SYZ trend, at least in my terminology, of which essentially the first step I like to put in the as first step is Guilhem and Sternberg, even though it's not historically correct. I think the SYZ program didn't exist in 1982. Please, someone more senior could correct me if I'm wrong. But what I mean by SYZ trend is that they describe a map from the type A Gmod P, so for example, Grassmanians to some larger N, whose image is a moment polytope. And the fibers of this map are generically Lagrangian tori, so something you would expect from an SYZ fibration. But so one of them, for example, is the so-called Gelfand Zeppelin torus. But there are more interesting fibers as well, just like you would expect in the SYZ picture. And for example, Cho, Kim, and Ho studied the topology of the fibers that sit over the boundary of this polytope. And they discovered that there are some Lagrangian fibers, unlike the toric case, that sit over the boundary of the polytope, and they have an interesting topology. And Hong, Kim, and Lau studied Lagrangians that are nearby these non-torus fibers. So some immersed Lagrangians in Weinstein neighborhood of these non-torus fibers, and they study their obstruction, their Markov spaces, and they were able to identify them with certain subschemes of the mirror. Okay, there is a third trend in which I feel I belong, which I call divide et impera trend. So it's an attempt to I think it starts with the work of Nohar and Ueda, which proved that the Grassmanians 2N contain actually lots of Lagrangian tori, and so they have a construction of Lagrangian tori starting from the data of some triangulation of an angle, and they showed that the dispotentials of this Lagrangian tori can be explicitly computed, and in particular, there are some transformations of triangulations of polygons that are called flips, and they correspond to transitions between these potentials of Lagrangian tori, just like you would expect in the wall crossing formulas for Lagrangian fluid theory. But I call it divide impera because somehow these tori are not the different fibers of a single fibration. Rather, their construction is a construction of multiple fibrations on the same space, the Grassmanians 2N, of which these are fibers, and somehow that's why I call it divide impera. Okay, so I'll describe two sets of results. One, which I call bootstrap results, in the sense that bootstrap, the idea is to come up with some generators for the Fukaya category, just like some non-zero objects, and see how much of the Fukaya category they split generate. So the goal, as I said, the end goal would be to come up with a collection of Lagrangian tori that split generates in general. So bootstrap is the simpler problem of coming up with at least one torus that generates part of the Fukaya category. Okay, so first of all, let's describe the spectrum of this operator C1 star that I described earlier. So I'm calling I a subset of nth roots of unity or half roots of unity, depending on the parity of K. And it turns out that the spectrum of this operator can be described as follows. It's the set of all sums of such roots of unity scaled by n, as I ranges over subsets of size k, where k and n are the parameters of our Grassmannian. And so here are some pictures of how this spectrum looks like in some cases. So here it's a projective space, CP7, and you'll see a circle of dots, just like in the example for CP2, we had 3 dots. But if you take larger Grassmannians, for larger K, you get some interesting patterns where you have multiple radii, and some of these dots also have high multiplicity, meaning there are many critical points, the multiplicity of these eigenvalues is higher. And the way this spectrum is computed is essentially a calculation in Gromov-Wheatstone theory. There is a basis of quantum cohomology parameterized by these sets I, where the set, the class sigma I is a sum over certain diagrams I'm listing later, called Young diagrams of Schubert classes of diagram D, and scaled by some values of Schur polynomials at roots of unity. And the remarkable property of this basis is that it diagonalizes multiplication by any Schubert class, and the eigenvalues are precisely Schur polynomial set roots of unity. And so C1 is a special case of this. So here are some examples. Grassmannian to 4. So the mirror is constructed in this way. You take, here I'm following the recipe of Marsh and Rich, which is again a special case of earlier work of Rich and Peterson. So you take the dual Grassmannian and you remove a divisor cut out by the 0 locus of these denominators here. So these coordinates are Plucker coordinates, which can be thought as coordinates in a projective embedding of the Grassmannian, and they're indexed by Young diagrams. So in this case, Young diagrams in a 2x2 box. There are 6 such diagrams, and some of them are declared frozen. Essentially, they're circular shifts of this full diagram. So if you remove a divisor cut out by this, there is a rule to work out a corresponding numerator for each of these denominators. And this rule has been found by March and Rich. And what you end up with is this function on this Grassmannian minus a divisor. And this is a picture of the critical points and critical values of this function. So in this case, there are 4 critical values with 1 critical point above it and 1 critical value at 0 that has 2 critical points over it. Yeah, and similarly, here's a different example, Grassmannian to 5. So for the mirror, again, you take the dual Grassmannian 3, 5. You remove a certain divisor. That's why I'm putting a bullet here. And the divisor is again cut out by the 0 set of these denominators. And there is a combinatorial rule to work out some numerators for this Laurent polynomial. And that's the prescribed or the candidate Landau-Ginzburg model. And here's a picture of its critical values and critical points. Okay, so let me see, how am I doing? Pretty good with time. Okay. Okay, so the first theorem I'll state says the following, that if you take for any Grassmannian this function that Marsh and Rich introduced, this W on the candidate Landau-Ginzburg model, and you restrict it to a suitable torus chart, so some open subscheme of this mirror, what you get is the dispotential, the Maslov-2 dispotential of a fiber of the Gelfand-Zetlin integrable system, a Lagrangian torus fiber of the Gelfand-Zetlin integrable system. To be precise, the monotone fiber, the monotone torus fiber. So the chart, let me say a few more words about this chart. So there's an open torus inside the dual Grassmannian, so whose dimension is the full dimension, so it's open. And it's given by the condition that certain Plucker coordinates do not vanish. And if you have ever seen cluster algebras, this is something typical that people doing cluster algebras. These are algebras with a specific set of generators, and these sets come in groups called seeds. And in this case, the seed is given by the Plucker coordinates parameterized by Young diagrams that are rectangles as opposed to more complicated shapes that are maybe segmented. So this chart has been, or this seed, if you want, has been highlighted in the work of Scott, which was the person who proved that the coordinate ring of the complement of this device in the Grassmannian has in fact a cluster structure. So if you want, another way to think about this result is saying that if you take the cluster structure that people already knew on the coordinate ring of this mirror to the Grassmannian, and you take the initial seed, meaning like the part of the natural data that defines the cluster structure, that defines a torus, complex torus that is mirror in this sense to a fiber of the Gelfand-Zetlin system, which is this candidate SVZ fibration on the Grassmannian. Yeah, so the way this theorem is proven is essentially a calculation. It's not really conceptual. So the way it's proven is by considering a toric degeneration of the Grassmannian to a singular toric variety, which is the toric variety corresponding to the Gelfand-Zetlin polytope, which is the polytope that is somehow the base of this candidate SVZ fibration. And by using a result of Nishino, Noir, and Ueda that studied what happens to do I have a picture of this toric degeneration? No, I should have put one. I'll have a picture later. But so what they did was to study how these potentials of Lagrangian tori degenerate under toric degeneration. And so essentially, their general result is specialized in this case to do this calculation of the right-hand side. And then to have the equality, essentially, the whole work is to guess the correct cluster chart. And the fact that this is really an equality up to an automorphism, because when you write down the dispotential of any Lagrangian as a Laurent polynomial or away from the monotone case as a power, as a generating function, possibly with infinitely many terms. So implicitly, you're always choosing some basis of cycles for your Lagrangian, which will allow you to turn boundaries of gelomorphic disk into some Laurent monomial or more complicated monomial. So it wasn't clear. It is not clear a priori what, even if you have a candidate Lagrangian torus, what basis you should work with. And in fact, in this case, the thing was that the basis that you naturally get from the fact that this Gelfand-Zetlin torus is the fiber of an integrable system is not the one that gives you this equality. So that there was a change of coordinates that happened to be a bit non-trivial. Okay, in any case, that's an indication that the Lagrangian this Lagrangian torus has a mirror. And so from this, you can prove the following. So if the absolute value, if you look at summands of the Fukaya category, where the absolute value of lambda, the charge, is maximal, or if you look only at Grassmanians where n is prime, then you can actually prove homological mirror symmetry. You can prove that this single Lagrangian torus, the Gelfand-Zeppelin torus with a bunch of local systems on it, gives you enough objects to split generate the whole Fukaya category. Yeah, so yeah, and some observations that were useful in proving this theorem were the fact, for example, that there's a dihedral group action on the mirror that somehow acts on the critical points, and so and this W that was known earlier is actually equivariant the level of critical points with respect to this action. So that tells you that if you're lucky enough to find an object of the Fukaya category that split generates this summand, let's say, then you can use this action to cook up objects that generate all the summands obtained by rotating this eigenvalue. And same story, if you hit maybe some inner summand here, you can use this symmetry to cook up objects that generate all the summands that that fall in the same d-n orbit. Yeah, and what emerges also from looking carefully at the spectral decomposition is the fact that there's always a summand that unconditionally is split generated by the Gelfand-Zeppelin torus, and it's obtained as follows. If you take, remember that these points are eigenvalues of the eigenvalues I described earlier. Maybe I'll go back to that slide. So these are numbers that are sums of root subunities scaled by n, and sums over a root subunity in sets of size k. But there's always k closest root subunity closest to the unit, which is certainly a root of unity. And so if you take the sum of those, something peculiar happens. It happens that this is always a positive real number. And somehow there is always a positive summand, and this is always generated by this torus, and so all the maximal ones are also generated. Yeah, but as you see from these pictures, there are some summands that are not in general split generated by objects supported on this torus alone. So for instance, here you see already in G26 some summands here that are not covered by these objects. Okay, so and maybe I'll add a picture. So essentially what's happening here is that we realize that there is a torus, the Gelfand-Zeppelin torus, that is mirrored to a certain chart, which I called T0 in the previous theorem of the mirror, but the mirror is larger. And this function W has some critical points, some of which fall inside your chart and some others possibly escape. And so the philosophy is that if you interpret the dictionary I presented at the beginning seriously, then you should deduce from this that when all the critical points fall inside T0, then you should be able to split generate the whole Fukaya category with the Gelfand-Zeppelin torus. And when it doesn't happen, then you shouldn't. And so that's essentially what I checked. For example, in the prime case, you can prove that all the critical points fall inside T0. And you can also prove that the critical point sitting over this critical value always falls inside T0 and all its orbit falls inside T0. Okay. Okay, then I'll describe a second set of results, which I call mutation. So the idea is the following. It has to do with this notion of mutation that people that have studied cluster algebras have introduced. So I'll give a brief introduction to what this means. So as I said, this chart T0 mirror to the Gelfand-Zeppelin torus is defined by the non-vanishing of certain Plucker coordinates on the mirror, and they're indexed by these rectangles. But these rectangles actually fit in a quiver, which was, again, described by Scott. And something you can do to a quiver is quiver mutation. And here I gave an example of quiver mutations. So we start with, I think this is the initial seed corresponding to the torus T0 for the mirror to the Grassmannian 2,5. And something you can do to this is a quiver mutation at a given node, let's say this box. And so once you do that, so I'll illustrate here how it works. The way it works, it's purely algebraic. So you look at all paths of length 2, for example, this one, that pass through your node, the node you're mutating at. And if any such path connects at least one node that is not blue, then you add an arrow. So this would be a new arrow. And similar story here, I have a length 2 path that connects 2 blue things. So I'm not adding that path. But then I guess I don't have any more here. Yeah, and then you flip the direction of all arrows that touch the mutating node. And last, you remove all oriented 2 loops that you created by this procedure. So you don't need to understand this in detail. It's just to convince you in an example that it's something purely algebraic from the quiver. So you get a new quiver with same labels, and then you update the label at the node you mutated by the following rule. So the new label, which in this example is this label here, satisfies the following property that when you take the product with the old label, then you get a sum of 2 terms. One is the product of the labels of incoming arrows, so this and this. And one is the product of labels of outgoing arrows, so this and this. Okay, so again, a purely algebraic rule. So you can either think of the new label as a Laurent polynomial if you divide by this. You can think of it either as a Laurent polynomial in the old labels, or remembering that these are really Plucker coordinates, and so regular functions on your mirror, you can work out the algebra in that function field and realize that this is actually, again, a Plucker coordinate. Okay. Yeah, and in fact, this formula gives you a birational map between 2 tori. One is T0, which is the torus defined by the non-vanishing of Plucker coordinates labeled by the nodes of the first quiver. And one is T1, which is, again, another torus in the mirror, which is labeled by, which is defined by the non-vanishing of the Plucker coordinates labeled by nodes of the second quiver. Okay. Okay, so this map ends up being a birational map of tori. And once you have this map, so you have a way to iterate this procedure, and you can also push forward your Laurent polynomial defined at the beginning along this map and get new Laurent polynomials. So here I gave examples of a mutation with 5 steps that starts and ends at the same quiver, and how the restriction of W, so what I call W0 is really the restriction of W to T0, and W1 is the restriction of W to T1, and so on and so forth. And so you can think of them either as restrictions, this global function, or as mutations of a single Laurent polynomial as you move along these charts through the mutation instructions of this quiver. Okay, so I hope that conveyed the idea of mutation. It takes a bit of time to get used to. But essentially, the construction I worked out is a construction that for any so-called Plucker seeds, which essentially is one of these quivers I drew, constructs a Lagrangian torus in the Grassmannian. And this torus is also endowed with a basis of cycles for H1, H lower 1, one for each Plucker coordinate inside the seed that you're working with. And this torus also counts with a local system, one for each set of size k of nth roots of unity. So remember, these were the ones that parameterized the critical points of W. And this local system is, I denoted by Ci, is defined by the following property, that the holonomy around this cycle is the number you get by evaluating the Schur polynomial, a certain symmetric function called Schur polynomial associated to the diagram that is somewhat well known in representation theory. And you evaluate that symmetric function on this set of roots of unity. You might hit 0 sometimes when you do this evaluation. In that case, the local system is not defined. But if you never hit 0, then it's defined. Okay. So the way this construction goes is by using an idea that was, I think, pioneered by WD1, but I'm actually using some work of Harada and Kabe. And so the idea is that anytime you have a Tark degeneration of a variety, in this case, a Grassmannian, so you should imagine it as a family over C whose fiber over 0 is a singular Tark variety and generic fiber is the Grassmannian. So anytime you have that, then the smooth locus of the singular Tark variety colored here in green can actually be flown back with a natural vector field to an open set in the analytic topology of X that is symplectomorphic to this region here. And in particular, all the moment fibers of the smooth locus of this Tark variety also flow back here, and they give you Lagrangian tori. Yeah, so, and what was known, there's a general construction, and what was known before, thanks to the work of, before my work, thanks to the work of Rich and Williams, was that, in fact, any of these seeds of the mirror, for algebraic reasons, essentially gives you a Tark degeneration of the Grassmannian. And in fact, you can interpret these Okonkov bodies that I was mentioning earlier, polar duals to Newton polytopes of these Laurent polynomials as moment maps images of these singular Tark varieties. So this was known. It was known that the Grassmannian has plenty of Tark degenerations parameterized by seeds of a mirror. And by just combining that with this result of Harada and Kabe, you get this Lagrangian tori and then you work out more carefully how these coordinates work, and you can also define the local systems and the cycles. Yeah, so here's a picture where I'm drawing, you should imagine a random walk, which actually coded. You find the link to the code on my website. So you can define a random walk on the set of charts, of torus charts of the mirror to the Grassmannian. So maybe let me again draw a schematic picture. So you have a bunch of charts, for example, this, and you can define a random walk that starts from the chart that I call T0, that somehow it's dual to the Gelfand-Zeppelin torus, and using these quiver mutations moves you along other charts. And as you go through, you can compute explicitly these Laurent polynomials and see what you get. And so these graphs are really maps of the cluster structure of the mirror. So each node is a complex torus chart, somehow mirror dual to one of these Lagrangian tor in the Grassmannian. And each edge is representing the fact that you can move directly from one chart to the other with a single quiver mutation instead of just a sequence of them. And so for the mirror of 2.5, it's pretty boring. It's just a cycle of 5 charts. But if you already do 2.6, it gets quite interesting. You see this there are some there are some charts that are pretty far. This and this, for example, and you go on, and this is what you get. You alternatively through mirror symmetry, you can think that these graphs depict a collection of Lagrangian tor in the Grassmannian, each are related, with some natural notion of mutation among them that is depicted. The relation of mutation is depicted by this graph.
And sorry, I missed, what do you accomplish by doing these random walks?
I'm doing the walk randomly because I wanted to show you, it's not part of the theorem. This is illustrative, okay? So what I claim and what I'll discuss later is that these Laurent polynomials are interesting, and sometimes they're dispotentials of this Lagrangian tori. Sometimes they're possibly not. And studying the coefficients of these polynomials, Laurent polynomials, might be interesting for Floer theory of this Lagrangian tori and investigating the Fukaya category of the Grassmannian. But it's just useful to have a list of those polynomials. And with this kind of random walk strategy, you can really produce a list where you can explore the behavior of these Laurent polynomials. So it's not part of the construction. It's something independent. I just put, somehow I just put it next to it to illustrate what's going on.
Thanks.
Yeah. So, yeah, and indeed, that's what I just mentioned. So for k equal 2, in fact, I could check that this Laurent polynomial, for k equal 2, it was checked, not by me, but by Noir and Ueda, that these Laurent polynomials are in fact Maslov 2 dispotentials of this Lagrangian tori. And the way they prove it is again by appealing to this result of Nishino, and Ueda, that says that if the torque degeneration degenerates to a variety that is not too singular, in the sense that it has a so-called small resolution of singularities, then any Maslov 2 disk, potentially escaping here, actually corresponds to a Maslov 2 disk that doesn't intersect the singular locus of this variety. And so you fall back to the case of smooth torque Lagrangian Floer theory. Lagrangian Floer theory for moment fibers of smooth torque varieties. Yeah, so but so essentially they could check that for k equal to this more resolution always exists for any targeted generation. And so a consequence of that I explored is that if n is of this form, a power 2 plus 1, then there is a natural such torus, which I like to describe with this triangulation of an angle, which I call dyadic or diadic, I'm not sure how to pronounce it, such that that single torus split generates the whole Fukaya category. And that's particularly interesting, I think, already in the case of, I think the Grassmannian 2.9 is already an example where the Gelfand-Zetlin torus doesn't split generate, but this Lagrangian torus does. And what's happening here is, again, if we go back to the picture I was drawing earlier, what's happening is that you have multiple cluster charts of the mirror. The critical points of W, the lambda Ginzburg potential, they fall somewhere with some non-trivial distribution among these charts. And what happens is that some of these charts contain only some of the critical points, whereas this peculiar chart that I'm describing correspond to is in fact a chart that contains all the critical points. And so you find this big fat chart, which is it contains more critical points than the others. And through this construction that I was describing, that corresponds to a Lagrangian torus that split generates the Fukaya category. And from this, essentially automatically also follows homological mirror symmetry in this case, because in this case, all the summands of quantum cohomology of one dimension and previously known generation criteria apply. And I have also other examples which I think are fun. So if n is any number such that when you factorize in primes, 2 is not a prime, 2 is not in the factorization, so any odd number, and and you write the factorization, and so what I'm claiming is the following: for each prime showing up in this factorization, I define a notion of triangulation of an angle that avoids that prime, and what that means is the following. If you think of this diagram as an angle, in this case an angle, for example, for each edge of this triangulation, you can look at the difference between the indices of its endpoints. In this case, for example, 5 minus 1 is 4, and 9 minus 5 is again 4, 5 minus 3 is 2, and so on. So we can define a triangulation to be prime avoiding if none of its edges have an index that is divided by p, the prime p you're working with. And so, and you can prove this theorem, which is fun. At least it was fun to work it out. That if you look at the factorization of n, and there exists triangulations that are prime avoiding for each prime in this factorization, then the corresponding Lagrangian tori split generate the Fukaya category of the Grassmannian 2n. And this is, for example, the Grassmannian 2.15, I think, is the first example where I don't think you can find any single torus that does that, but with two of them you can. And this is because like 15 is 3 times 5. Yeah, okay. Yeah, and in fact, you can look at the Newton polytopes of these Laurent polynomials. And since the construction I defined earlier works for any Grassmannian, what doesn't work for any Grassmannian is this statement that these Laurent polynomials are on the nose, these potentials. But the construction works in general, and you can look at these Laurent polynomials and compute their Newton polytopes, for example, and their number of critical points. And if you can check that some of these Stark varieties that appear as Stark degenerations of the Grassmannian have a small resolution on singularity, essentially the same arguments above will imply that these are, in those cases, these potentials. And so in the here's a picture in the Grassmannian 3.6. So there are like 34 charts that correspond to 34 Lagrangian tori. This will be my last slide. So the first one is somehow the Gelfand settling. And then all by these two can be checked to correspond to Stark degenerations with a small resolution of singularity. And here, this is essentially data that describe which cluster you're working in. And these are phase vectors of the Newton polytopes of the corresponding this potential. And these are numbers of critical points. And so from tables like this, you can prove theorems like, and this is purely, this is just a sample things. And the construction really works in general. So, but for example, you can say there are 6 monotone, non-displaceable Lagrangian tori in the Grassmannian 3.6. And the way you do it, again, you start from the Gelfand settling torus, you do these quiver mutations, and then they give you candidate Maslov to these potentials by mutating this initial this potential. And if you can check that the corresponding Stark varieties has a small resolution, then they are in fact through these potentials, and you can use them to distinguish these Lagrangian tori. And what's actually conceptual is that maybe this will be my final remark, is that one of these critical points is quite special, and I think it would be interesting to study in general in the final case. But there is always this critical point that sits over this positive real eigenvalue of maximal modulus, and that somehow falls. You can prove that essentially by definition of cluster algebra, it falls in the intersection of all the charts. So proving that these tori are non-displaceable is essentially a conceptual proof, because you know by this positivity property that this critical point will be a critical point for all these potentials, and so you don't need to do any calculation. Instead, proving that they're distinct involves in general considering some discrete invariants of these potentials, like the Newton polytope, and that is a calculation. Okay, so yeah, I'll stop here. Yeah, I'm happy to answer questions.
Let's give Marco a hand. Okay, any questions for Marco? Maybe I'll start off with one. Are there any like patterns or formulas that you can give for that number of monotone non-displaceable Lagrangian tori?
Yeah, in general, no, because in general, there are infinitely many charts. This process that I described is really a process that potentially produces infinitely many Lagrangian tori, so you can't really count them. For the Grassmannians 2n, there are finally many, and their number is a Catalan number, and they're all monotone. So yeah, it's but this was essentially already. So your question in that special case was already answered by Noah and Weda. And I mean, it was previously known that the Catalan numbers enumerate cluster charts of the mirror of Grassmannians 2n by the people in cluster algebras. That's something somehow foundational. Yeah.
Okay, I see a question from Catherine Cannizzo.
So can you say what's involved in computing structure maps like the differential and composition for the Grassmannian, or is that packaged into what you described? So are you thinking of structure maps of the Fukaya category?
Yeah. Yes.
Yeah. Okay. Yeah. Somehow, I don't know. My goal here was to avoid the calculation. So even if you, for example, if you take two of the tori I talked about, and they are adjacent in the sense that they are related by just a single quiver mutation, then you might ask, I think a special case of your question is, can you describe, if you endow them with local systems with the same charge, can you describe somehow generators and differential of the Floer complex of the pair, something like that. And so I don't think it's I don't see any way to do it, and it's not done. I mean, I certainly don't do it. So the way these generation statements are proven is by arguing that these objects are non-zero. And for that, you just need to understand the dispotential and see that it has a critical point. And then essentially each local system that has this property that gives you non-zero Floer cohomology corresponds to an object falling in a given summand, depending on its charge. And then to argue that you generate, you just need to prove that you have enough for each summand. So if the summand of quantum cohomology with that eigenvalues is high dimensional, then this could be hard because if you need multiple tor, I don't think there is a good generation statement. It's known that if you have enough objects on a single Lagrangian torus, that generates that summand, but by work of starting from Abu-Zaid generation criterion and then Ganatra and I think also Sheridan had some work on this, but in general, like split generation follows from either knowing that the summand is one-dimensional, or knowing that it's maybe higher dimensional, but the objects that you want to generate with all are supported on the same Lagrangian torus. Yeah. And in fact, since in my abstract, I mentioned that this is part of a program to prove that the Fukaya category is split generated by Lagrangian tori. So I think, which is the closest to what to what I could define a calculation in your sense. I think for that purpose, so I think these are the right candidates for objects for generators, but you need to do some work to prove generation in general, precisely in those cases. So there are cases in which you have maybe like multiple critical points over critical value for W, but there is no single chart that covers all of them. So you need multiple charts that correspond to multiple Lagrangian tori that support a number of objects, and you want to prove that they generate that summand. Yeah, and to do this, it's a bit hard. So I think one has to introduce some new structural results about bulk deformation, split generation in the context of bulk deformed Fukaya categories. Because bulk deformation allows you to essentially wiggle these fibers so that the critical points now fall on have different critical values. And so in that case, every summand becomes one-dimensional. Yeah.
Thanks.
So I wanted to ask, do you think that your techniques might apply to any other homogeneous spaces?
Yeah, so in fact, yes, the answer is yes. This idea of torque degeneration is quite general. It actually applies essentially, whenever there is a theory, the theory of all-controlled bodies, that provides large classes of toric degenerations for essentially any projective variety. So yes, I think the similar arguments will produce many Lagrangian tori infinite manifolds, for example. But if you want to prove that, to compute that these potentials, or to prove that they split generate the Fukaya category, I think it's helpful to have not only that, but their existence, but that they are related by some kind of nice maps. And for that, it's really helpful to be in the cluster case. But as I said, G mod P has a cluster mirror almost in full generality. And so, yes, I would expect these techniques to generalize to that setting. Yeah, there are some complications. This trick of wiggling to make the spectral decomposition having one-dimensional summands essentially that might not work in full generality. I'm not sure, but maybe it will not work if you leave the Gmod P case. But yeah, for Gmod P, I think it's fine.
Any more questions for Marco? Okay, let's thank Marco again for a great talk.
Thank you for inviting.